All right, working on the homework for 4.3. Here's the first problem. Now these problems are pretty involved. All right, there's a lot going on here, so each one of these should take a while. But this is kind of one of the main concepts of this class. So consider the equation below. So we've got some function. It's defined on some closed interval 0 to pi, and we want to find where the function is going up, where it's increasing, where it's going down. Well, I should say this part is where we want to know where it's going down. We want to find any local minimum and maximum values, so where our graph would come down, local min, where it might go up, local max, and then find any inflection points, which would be where we have a change in concavity, where it goes from concave down to concave up, or where we might have something like this, where our graph goes from being concave up to concave down. So to do all of this, we're going to have to work with the first and second derivatives. So what I'd like to do to start is I'd like to take our function. I'd like to take its first and second derivative. So the first derivative of this, 7 is a constant, derivative of sine of x is cosine x. And then 7 is a constant, derivative of cosine x is negative sine x, so that makes it negative 7 sine x. Then I'll need the second derivative to work with the concavity. So take derivative again. Derivative of 7 cosine x is negative 7 sine x. And then the derivative of negative 7 sine x is negative 7 cosine x. All right, so here's the way that this is going to work. What we're going to do, once we've got all this information, we're going to take our first derivative, we're going to set it equal to 0. We're also going to see if the second derivative is undefined anywhere. Well, setting it equal to 0 results in setting 7 cosine x minus 7 sine x equal to 0. We will not have to worry about where it's undefined because we can cross this out, because our derivative is made up of sine and cosine, and they're being subtracted, so both of those are continuous functions. So we have a well-behaved derivative. So we're only going to look at where it's 0. So when I set that to 0, I can move the sine x to the other side, 7 sine x to the other side. Divide both sides by by 7. I get cosine x equals sine x. So what I could do now is I could try and determine when sine x is equal to cosine x. That would give me every place that my derivative is 0. So if I go back to the unit circle, go to the idea that if we have an angle, that the x-coordinate is cosine of that angle and the y-coordinate is sine of that angle. So we're basically asking ourselves with this equation, when on the unit circle, at what angle are your x and y coordinates the same? And also, we need to make sure we're looking just between 0 and 2 pi. So if you go up here to pi over 4, we know we have root 2 over 2, root 2 over 2. So the x and y coordinates are the same, which means cosine and sine are the same there. So pi over 4 would be one angle. And if we go directly across from that over here, we get negative root 2 over 2, negative root 2 over 2. There the x and y coordinates are the same. The angle here is 3 pi over 4. So I have two places where my derivative is 0 in this interval. So what I recommend you do from here is you draw a number line. Now we are restricted between 0 and 2 pi, so I'll restrict us here. Let's mark some points here. Here's pi, pi over 2, 3 pi over 2. The angles we're talking about where we had our derivative was 0 was pi over 4, which was here, and then 3 pi over 4, which is here. So what we need to do now is we need to break up our number line into, in this case, it'll be, because we are going to stop at 0 and 2 pi, we have 3 regions, right? We have region 1, region 2, region 3. What I need to do is figure out if my function is going up or down on each of these regions, even over here, up or down. And to do that, what I will do is I will pick a test point. So my test point, I'm going to do this in black, can be any point in this region. So I can pick something, anything I want over here. So let's say pi over 6, I know lives there. And then I can pick something like pi in here. And my third region, I'll pick 3 pi over 2. And what I'm going to do is I'm going to plug these values into the derivative. Now the derivative, remember, was up here. Where was our derivative? Right up here. Okay, notice I'm not plugging it back into the function, plugging into the derivative. So I want to know, first of all, what is f prime of pi over 6? Well, that means I want 7 cosine pi over 6 minus 7 sine pi over 6. Cosine of pi over 6 is square root of 3 over 2 minus 7 times sine of pi over 6 is 1/2. And if you figure out what this number is, you'll determine that it is a positive number. And what that means is that in this region, in this interval 1, in that, not interval 1, but in that first little region there, my derivative is a positive number, which means that my original function must be increasing there. So what I'm going to do is I'm just going to try and squeeze this in here. I'm going to put that over here, f, that's too thick, f is going up over here, increasing. Okay, now I need to test the same thing in the second region. So I picked my pi was what I was going to use. F prime of pi is 7 cosine pi minus 7 sine pi. And cosine of pi is going to give you -1, and then times 7, so that's -7. Sine of pi is 0, so that's just -0. And that's a negative number. So what I know is that on that second region, here's what I'll do. This was on that first region. On that second region up there, my derivative was actually negative in that region, which means that my original function is going down there. So I'm decreasing there. And then I'm going to look at the last region, which is our third region. And we had picked, let's see, 3 pi over 2 as our test point. So I want to know what the derivative's value is at 3 pi over 2. So that's 7 times cosine 3 pi over 2 minus 7 sine 3 pi over 2. So what we get here is cosine of 3 pi over 2 is 0, so that whole thing's gone. And then over here I get -7, and then sine of 3 pi over 2 is -1, which means that we have a positive number. Negative times negative is positive. That tells me that on that third region, my derivative is positive, which means my original function is going up. Now you might be saying to yourself, do I really have to test all these points? Because it just went and it was increasing, then decreasing, then increasing. Will it always alternate back and forth? So the answer is no. Sometimes it will go from increasing to increasing and then to decreasing, or it might be increasing all the time. So you must check these test points in each of the intervals. Big thing to remember, your test points are going to be, these points in blue are what you got when you set the derivative equal to 0. The test points are any points in the regions that were created by those points you found. So anytime you find these values in blue, it'll split your number line up into regions. And then depending on how many regions you have, will determine how many points you're going to test. Okay, so let's try and answer the first part of this. I want to know when I forgot to label this up here. On the second region, my graph was decreasing, and then on the third region, it was increasing. So let's talk about where f is increasing. F is increasing anytime we are between 0 and pi over 4, and anytime we are between 3 pi over 4 and 2 pi. So the way we'll say that is 0 to pi over 4, and then we could use a union symbol 5 pi over 4 to 2 pi. 3 pi over 4, sorry. Holy crap, I just realized that I picked a point that was in the wrong place. Oh my gosh. I just realized I did something very stupid. But it's okay, it's not going to affect anything. This right here was 3 pi. This 3 pi over 4 is actually that angle right here. It's 5 pi over 4. And this was drawn correctly but labeled wrong. So this is 5 pi over 4. Now, the good news is that our test point, 3 pi over 2, is still okay. Had I used something else inside that wouldn't have worked. Like if I would have tried to use pi over here, but we're all good. That was just, I just wrote it down wrong. Okay, so we're increasing from 0 to pi over 4, and then also from 5 pi over 4 right here to 2 pi. All right, sorry, I don't want to go back and redo that whole video just for that little thing, so I'm going to keep it. All right, now, next thing, all right, we found out where it's increasing. We need to write down where it's decreasing. So f is decreasing, and that's happening here in this blue region. So that is between pi over 4 and 5 pi over 4. All right, so that's it. We've answered the first part of this. Now the next part of it is asking to find local minimum, local maximum values. So to do that, I want to look at anywhere where my function is defined and it goes, let's say for local minimums, it'll have to go from decreasing to increasing. For maximums, it'll have to go from increasing to decreasing. So let's start with this right here. I actually do have that happening here. I go from decreasing to increasing, and that's happening at 5 pi over 4. And my original function is defined at 5 pi over 4. My derivative there is 0, so I do know that that point does exist on my graph. So I should have a local minimum there. So I will say f of 5 pi over 4, which when you plug 5 pi over 4 into the function, I'm not going to show the work, but when you plug 5 pi over 4 in, you get negative 7 root 2, which is approximately negative 9.9. This is going to be your local minimum. And then for local maximum, we're trying to figure out if there's a place where we go up and then down. And that is happening right here. We go up and then we come down right here. So that happens at pi over 4. Our function is defined there. Our derivative is 0 there, so I should have a local maximum there. So f of pi over 4, and again, I'm not going to show that work, but if you plug pi over 4 in, you should get 7 root 2, which is approximately 9.9. And this is going to be your local max. All right, so we have answered part B of this thing. Let's see. Local min, local max. Now, find the inflection points. Also find the interval in which f is concave up and where it's concave down. So all of this inflection point stuff and concave stuff is all going to be coming from second derivative. So now what I need to do is I basically need to repeat this entire process I just did, but for the second derivative instead of the first. So I need to work with this. The second derivative being negative 7 sine x minus 7 cosine x. So I'm going to start a new page. My second derivative is negative 7 sine x minus 7 cosine x. And what I need to do with that is figure out where the second derivative is 0 and where the second derivative is undefined. Now, I don't have to worry about undefined. Just like before, it's a nice trig function. So it's with sine and cosine in it, so it's defined everywhere. What I do need to do is set this thing equal to 0. So I set negative 7 cosine x minus 7 cosine x equal to 0. See, negative sine x equals 7 cosine x. And you can divide both sides by 7, and you get negative sine x equals cosine x. Now before, what we were saying is, from this we were saying, when are the x and y coordinates the same? Here we're saying, when are the x and y coordinates off by a sign, right? They need to be equal but opposite in sign. So if I go to my unit circle again, I think about where does the x and y coordinate look exactly the same except their signs are different. So that's going to happen here, because here my x coordinate is negative root 2 over 2. My y coordinate is positive root 2 over 2. The other point where it's going to happen is right here, because my x coordinate is positive root 2 over 2 and my y coordinate is negative root 2 over 2. So you can see with both those points, they're exactly the same, but they're different in sign. Let's see if I can get my angle right here. Can't believe I did that earlier. All right, 3 pi over 4. That's where 3 pi over 4 is. And this one is 7 pi over 4. I'm sure about that now. Okay, so what I'll do now is I'll draw a number line. Now remember, in this problem we were going from 0 to 2 pi. We were restricted on that interval. It's not always the case, but in this problem it is. So here are some of the important points. Now, where are we? We've got 3 pi over 4, which should be here. And then 7 pi over 4, which should be here. This breaks up my number line. And then remember, I cannot go past 0, can't go past 2 pi. So again, I have 1, 2, I have 3 regions. So I will pick a test point in each region. So how about pi over 2 is 1. Here pi is another test point, and then I got to pick something in here. So you could try, you could use your unit circle if you didn't remember what these were, but 11 pi over 6 is an angle over there. It's this one right here. It's negative 30 degrees, negative pi over 6. So those are the 3 test points that I've picked. Each one of them lies in those 3 regions, and now I will plug those into the second derivative up here. So let's see what happens. If I take f double prime of pi over 2, plug that into my second derivative, I got negative 7 sine of pi over 2. And I get minus 7 times cosine of pi over 2. And what we get here, sine of pi over 2 is going to be 1. So then times negative 7, so I get negative 7. Cosine of pi over 2 is 0, so that's gone. So I just get negative 7, which means that this is a negative number. And what that tells me is that the second derivative is negative on this region. And that tells me that the original function is concave down. So it looks like a frown on that region. Now, I don't know what part of the frown it is, but I know for sure it looks like a frown. Okay, so now I need to plug in the next one, f double prime of pi. So when I plug that in, I have negative 7 sine pi minus 7 cosine pi. Okay, sine of pi is 0, so that's gone. Cosine of pi is negative 1, so I get negative 7 times negative 1, which is positive 7, so that's greater than 0. That means my second derivative is greater than 0 on that region, which means that my original function is concave up. Again, you might be thinking, hey, is it always going to switch? No, it's not. Last test point, 11 pi over 6. Plugging that in. Negative sine of 11 pi over 6 minus 7 cosine of 11 pi over 6. So sine of pi over 6 is the y coordinate at that place. at that angle. So the y-coordinate there is -1/2. So 7 times -1/2. Then over here I have -7. Then cosine of 11 pi over 6 is the x-coordinate there, which is √3/2. Now let's see, we're going to have negative and negative. That should all be negative, so that should be less than 0, which means my second derivative is less than 0 there. And if it's less than 0, then that means my original function is concave down there. All right, so coming back up to here, I went concave down over here, concave up in here, concave down over here. So I'm supposed to figure out the intervals where I'm concave up and concave down. So I'm concave up here. I'm concave down here. My inflection points happen anywhere I have a change in concavity. So I go from down to up or up to down. Here I go from down to up. That happens at 3 pi over 4. Then on the next one, I'm up over here and I go down here. That change happens at 7 pi over 4. So my inflection points are happening at x is 3 pi over 4 and also at 7 pi over 4. And then finally, I'm concave up on the interval 3 pi over 4 to 7 pi over 4. I'm concave down remember it was 2 regions, this one and that one. So from 0 to 3 pi over 4, and then also from 7 pi over 4 to 2 pi. Okay. That should be it. Let me see if I'm missing anything here. Inflection points, got those. Let's see, inflection points, yeah. Got the concave up, concave down. Yeah, all right. So that should do it for that. I'm going to take a quick break. That problem took way too long. Let's see. See exactly how long that took. 22 minutes. Okay, this next problem, consider the function here. Find the intervals where it's increasing, where it's decreasing. Find any find the local minimum value of the function, and then find the interval where it's concave up. All right, so let's get to work on this. Oh, that's not going to do it. Okay, so our function here, f of x equals e to the 3x plus e to the negative x. All right, so let's start out here with getting our first and second derivatives. Our first derivative, okay, we have 2 terms, so we're going to do them separately. Derivative of e to anything is itself, and then times the derivative of what's up in the exponent, so derivative of 3x is 3. Then plus derivative of e to anything is itself, times the derivative of what's up there, which is -1. Clean that up a little bit. That's 3e to the 3x. I just make this minus e to the negative x. All right, that's my first derivative. Now my second derivative, I just take derivative of this now. So the 3 stays out there. I take derivative of e to the 3x, which I already know is 3e to the 3x. That 3 is going to hit this one and become a 9. E to the 3x. And then here I'm going to subtract, but I already know that derivative of e to the negative x is negative e to the negative x, so the negative will become a plus. So there is my function. There's its first derivative. There's its second derivative. So to figure out where it's increasing, decreasing, I'm going to take the first derivative, which I think I'll just write it down here for a second. It was 3e to the 3x minus e to the negative x. I want to know when that's 0. I want to know what's undefined. So let me start by setting it equal to 0. If I set it equal to 0, I think I'll do that work over here. 3e to the 3x minus e to the negative x, when is that 0? Well, that means when does 3e to the 3x equal e to the x? And now I've got somewhat of an interesting situation here. Oops, negative x over there. I got to kind of look at this and figure out what's going on here. That might help if what I do is I rewrite this as 1 over e to the x on the right side, and then realize what I could do is multiply both sides of this equation by e to the x. If I do that, I get 3e to the, now if I have the same base e and I multiply them together, I'm going to add the exponent, so x plus 3x is 4x. Then on the right side, I get 1. Now, yeah, because they cancel. So now I'm going to divide both sides by 3. E to the 4x has to be equal to 1/3. Now I'm going to use properties of logs that says that if I take log of e, it'll kill the e, and that 4x is going to drop down, but I got to do that on the right side too. So I get 4x over here, because these kill each other off, equals natural log 1/3, and then I can multiply both sides by 1/4. 1/4 natural log 1/3, and make sure that 1/3 is trapped. You cannot multiply times that 1/4. So that's the value that will make my derivative 0. Now, was my derivative ever undefined? If I go back up here, take a look. The only thing I really have to worry about was this 1 over e to the x right there, this piece. But remember, this e to the x can never be 0, so I don't have to worry about division by 0. So this thing is always defined. I'm happy. So now what I'll do is I'll just draw a number line. And I will see, since I don't have a closed interval here, all I'm going to do is just pick a point here. And, or not pick a point, write down the only critical number I have, which was 1/4 natural log 1/3. And I'm going to need to figure out what that is in order to figure out, you know, where I am on the number line. I'm just going to use my calculator here. I'm going to go take natural log of 1/3 and then divide that by 4. And I get negative, this is approximately negative 0.275, let's say. Well, that breaks my number line up into 2 regions. So I've got this region here, this region here. All I have to do is pick any test point I want to the left of it and to the right of it. So anything I can think of, as long as it's in the domain of the original function, which, by the way, the original function is always defined, so I can pick anything. How about 0? 0 would be over here to the right of a negative number, and then over here I could pick like -1. And then what I'm going to do is I'm going to take those values and I'm going to plug them into the derivative. So I want to know what f prime of -1 is. Now remember, f prime's right here. So I'll use this one right here. So what I'm going to be doing is 3e to the, let's see, 3 times -1 is -3. Then minus 1 over e to the -1. So this is the same as 3 over e cubed minus, that's just e right there, because that comes up. I can already tell you that that's going to be a negative number, because 3 over e cubed is a really small number. And if I subtract e from it, I should get something that's negative. So I should have a negative number. You can confirm that on your calculator. The derivative over there is less than 0, means that the original function is decreasing over there. So I know that over here to the left, I'm decreasing my original function. So I'll go ahead and put that down. I'm decreasing over here. F is decreasing over there. And then I can plug 0 in to the derivative. So if I plug in 0 to the derivative, I get, let's see, up here, this will be e to the 0. E to the 0 is 1, so I just get a 3. Minus 1 over e to the 0. E to the 0 we already said was 1, so that's just 3 minus 1. That's 2. That's a positive number. Derivative is positive. That means our original function is going up over here, increasing. So back up here, I'm increasing over here, my function. So I think I can answer the first question. I wanted to know where it's increasing and where it's decreasing. So my original function, f, is, I'm just going to say this for increasing and say this for decreasing. F is increasing, let's see, over here, which started here at the 1/4 natural log 1/3. So from 1/4 natural log 1/3 all the way forever to the right. So we say till infinity, or to infinity. And then to the left of this means from negative infinity all the way until you get to that 1/4 natural log 1/3. And that's it for that. So the next thing I want to know is where was the local minimum. So notice that we had our function was going to go from decreasing to increasing, which means we'll have a local minimum here as long as that point was able to be plugged into the function and the derivative was 0 there. So let me see. Well, derivative doesn't have to be 0, but that our function must be defined there. So remember, our function is defined everywhere because we can plug any x in here and here. So that should be where we have a local minimum. So you can say that f of 1/4 natural log 1/3 is where you have local min. And if you plug that into the function, I would just plug in that decimal that we had, the negative 0.275. Just plug that in. You'll get approximately, let's see, 1.755. That'll be our local min. Okay, the last thing to do is to figure out where it's concave up or concave down. So now we're going to go work with that second derivative, which was right here. We're going to take a look at that. I'll go ahead and start a new page. So if our second derivative was 9e to the 3x plus e to the negative x, just make sure I wrote that down right. Yes. Then I would like to know where it's 0, where it's undefined. Well, for the same reason as the first derivative, it's defined everywhere. So I just want to know when it's undefined. So 9e to the 3x plus e to the negative x, I want to know when that's 0. Well, there's different ways I could explain this, but let me try it this way. Well, you know what? I think I can do it just with this. We know by the property of exponential functions that e to any power, this is always a positive number. Okay, that goes back to the whole idea of the exponential function looks like this. And, of course, it could go this way also, but as long as it looks like a to the x and a is greater than 0, a is not 1, then we're sure that it looks like one of those two up there. So we know that's a positive number because the graph of it's always above the x-axis. I know that this is also a positive number. And then what I'm going to do is I'm going to take 9 times a positive number, so that's going to be positive, and I'm going to add a positive number. And there's just no way that can ever be 0. So there's no way that this will ever be 0. What that means is that if I try and split my number line up, there's no point where it's going to go from concave down to concave up or from concave up to concave down. All it means is that it's always either concave up or concave down. It's one or the other. So all we have to do is pick any test point we want, like 0, plug it in to the second derivative, and see if it's a positive or negative number. So if we plug 0 in, e to the 0 we set up here, e to the 0 is 1, so we get 9, plus e to the 0 we already said was 1. So this is a positive number. That means we're concave up. That means we're always concave up, always. So it's asking in this problem, where is, in what interval is it concave up? Well, everywhere. How do we say that? Negative infinity to infinity. That's where our original function is concave up. So we are done with that. Okay, trying to figure out where this function is increasing, decreasing, where its local min is, where its inflection point is, where it's concave up, where it's concave down. So we got to go through all the work for this one. So f of x is x to the 7th natural log x. My first derivative, I'm also going to point out here that the domain of this, because we have a natural log function in there, the domain has to be from 0 to infinity. So we can't plug in 0, we can't plug in negative numbers into this. Just keep that in mind. Okay, now the derivative, product rule, 7x to the 6th times natural log x plus derivative of natural log of x, which is 1 over x, times x to the 7th. This is 7x to the 6th natural log x plus x to the 6th. And I think I will factor out an x to the 6th and then put 7 natural log x plus 1. Now, I just did that because I'd like to now take the derivative again and use the product rule again. So derivative of x to the 6th is 6x to the 5th, then times 7 natural log x plus 1. Now, derivative of 7 natural log x plus 1 is just 7 over x times 6x to the 5th. So I'm finishing off product rule there. We get 6x to the 5th. Notice 6x to the 5th appears, oh, you know what? Oops. Nope. Finish off product rule. This is just x to the 6th. And then I'll go ahead and go through 7 natural log x plus 1 plus 7x to the 5th. And each of those have an x to the 5th in them, so I'll factor that out. X to the 5th, and then what I'm left with is the 6, this 6 right here in front of these, so I'm going to multiply it through. What is that, 42 natural log x plus 6, and then what I was left with over here plus 7. So we get x to the 5th, 42 natural log x plus 13. Something like that. Okay, there's our first derivative. There's our second derivative. Now, at this point, I'd like to know where my first derivative is 0. Now, I also want to know where it's undefined, but the only place that this first derivative is undefined is when natural log of x is undefined, and that's going to happen at any x is 0 or negative, but remember the original domain doesn't have 0 or negative, so I don't have to worry about that. So I really only want to know where the derivative is undefined, or 0. So I want to know when x to the 6th, which is my first derivative, times 7 natural log x plus 1, when does that equal 0? So it's already factored, so I can set that to 0. That gives me x is 0. Throw that out. Why? Well, x can't be 0, domain of the function. So the only other place that it can be 0 is when 7 natural log of x plus 1 equals 0. So I'm going to do some algebra here, just move things around. Subtract 1 divided by 7. And now to get rid of natural log of x, we come in with e on both sides. E to the natural log of x equals e to the negative 1/7. E to the natural log of x on the left side drops out. You just get the x. And then on the right side, e to the negative 1/7. Believe it or not, that's a number, right? So what I'm going to be able to do now, and this is my only critical number, so be able to split my number line up. E to the negative 1/7. I'll go ahead and just grab my calculator real quick. Negative 1 divided by 7. E to that. 0.866 or 0.867, something like that. 0.867, I'll say. Okay, that breaks my number line up into 2 regions. I just need to pick a test point on each side. So why don't I go with 0 and 1? And let's see here. Plug those into the derivative. So what is the, oh wait, hold on, I made a mistake. Cannot plug in 0. Why? 0 is not in our domain. Right, here was 0, cannot plug something in there. So how about, I'm going to have to take something else. How about 0.5, 1/2, whatever. So what's the derivative at 0.5? So So what I need to do is plug 0.5 in to my derivative, which is this one up here. And I'll probably need a calculator for that, but I can probably simplify it. Let me try and do it up here just so you can see it. When I take 0.5, 1/2, and I raise it to the 6th power, I get a positive number. Times, now I just got to figure out if what's in here is positive or negative. So I'm going to take natural log of 0.5 on my calculator, then times 7. So natural log 0.5 times 7, then I'm going to add 1. I get negative 3.85. So I have a positive times a negative. This is a negative number. So what that tells me is down here, my original function, because my derivative was negative, is decreasing. Now if I plug in 1, plug 1 into this thing, 1 to the 6th power is 1. And then, check it out, natural log of 1 is 0, so that whole thing goes away. And all you're left with is plus 1 in there. And that's a positive number. And that means that my function is increasing here. So I can kind of summarize things here. F is increasing on the interval 0.867 to infinity. Now, you could have written, remember where 0.867 came from, e to negative 1/7, infinity. It's decreasing on the interval 0 to that e to negative 1/7. I have a local minimum, right, because it goes from down to up, at f of e to the negative 1/7, which you would have to plug into the function. I'm not going to plug it in. It comes out to approximately negative 0.053. So that's our local min. And then we need to go on and look at concavity and inflection point stuff. So I need second derivative. I need to work with that. So let me take that and work with it on the next page. I'm working with x to the 5th, and then it was natural log 42 natural log x plus 13. And I'm going to set that to 0. I don't have to worry about where it's undefined, because my domain doesn't restricts me, so I'm not going to be plugging in 0 into this or negative numbers. So just set each one equal to 0. That one equal to 0 only happens here, but I chunked that because that can't be my domain. So I need to figure out when 42 natural log x plus 13 is 0. Same thing as before. Isolate natural log of x, subtract 13, divide by 42. And then take e on both sides. If you do that, you get e to the negative 13 over 42. E to the negative 13 over 42. And I'm going to figure out what that is on my calculator. And I get 0.734, approximately 0.734. So what I'll do now is I'll split up my number line. Remember, 0 cannot be here, so I cannot plug I can't pick anything there. Here's my 0.734. I'm going to split it up. I have two regions to look in. I can still go, I can pick 0.5 again if I want. I can pick 1 again if I want. And if you plug those in without me actually going through this, I think I've done enough to show you. When you plug in 1, you should get positive second derivative, and when you plug in this, you should get negative. So it goes from concave down to concave up. So we have an inflection point right here. That's at f equals, remember that was e to the negative 14 over 42. Plug that into your calculator. Well, I don't have the decimal answer of that, so it's something. But that's the inflection point. And then where is it? Concave up, concave down. So concave up is from e to negative 13 over 42 to infinity. That's this. Concave down was this one. So it's down concave down, from 0 to e to the negative 13 over 42. Okay, I think I've got it all there. Let's see how much more I've got going on. So I've done 3 of these. I'm just looking at these here. What I'm thinking is that I'm going to just post the answers to these. Just the work, just what you should get as a result, and see if you can work those yourself. So I want you to take a moment to look. I've done the first 3. So here's my number 4. So just take a look at the function there. I'll zoom in so you can see it. Okay, there's my function, and I'm going to go through all the work here. I'll show you, I'll include that. And then here's my 5th one. Here's my 6th one. And here's my 7th one. Okay, so now I think you probably want to see the answers to these, so let me try and get you that. This is not it. Let's see, where did I put it? There it was. That's the one I just did. So I did that one. I didn't do that one. I'm not sure which one that was. You're going to have to go back and look. But here's the solution for it. Again, I'm going to make it kind of bigger, so you can kind of see it. Yeah, that's it right there. So that's for this function right here. And then we get to the next page. Okay, I think that was the next problem. I think this one was number 4. I'll have to zoom down just a little bit. Okay, so there's your function, there's your derivative. You can figure out where you're increasing and decreasing at, where you have local max and local min. There's your second derivative information, where you're concave up, concave down. There's no inflection point. Oh wait, there are points of inflection. Yeah, there's 2 of them here. And then there's a graph of it. Okay, that's another problem. These are out of order, I understand, but at least you'll have the answers. Give you a second there. And then that's the one from the very beginning. This is the last one. This is a long problem. Zoom this out. Make sure there's nothing else. Okay, so I'll just leave that up there for a second. So my idea here is that I've shown you, 3 or 4 examples now. And I'm hoping that with that, along with the lectures that I've done, that's enough to get you through these. Each problem is unique, like especially this last one. I can already tell you're going to have to be solving some trig equations. But the method that I've used is the same for all of these. So see how you do with those and let me know if you need help. Okay, I think that's good enough.